Okay. I think we're approaching 2:30 here, Helsinki time, and it's time to start the webinar. I want to warmly welcome you all to today's Industry and Society webinar organized by the Finnish Center for Artificial Intelligence. Now, today we're going to talk about empirical design of experiments with AI, which is a very fascinating topic. My name is Mikko Mäkelä. I work as a research professor in intelligent biomass processing at VTT, and am going to host today's webinar. We've been fortunate enough to manage to rally three excellent speakers for today's webinar. We have Arto Klami from Helsinki University and FCAI, and then Morten Bormann Nielsen from the Danish Technological Institute, and finally Søren Furbo from Novo Nordisk. But before I let these gentlemen deep dive to the actual topics, I suspect that we have some international guests or other guests who might not be that familiar with FCAI. So I'm just quickly going to present who we are, what we do, and then we'll jump into the actual webinar content. So FCAI is actually a flagship project funded by the Research Council of Finland. We started off in 2019 and am continuing until 2026. So we actually focus really on fundamental machine learning and unsolved machine learning problems. I think this figure nicely summarizes the structure of FCAI, where on the left-hand side, you see the fundamental research programs, which are mainly led by university professors and focus on data efficiency, trust and ethics, and understandability of AI. And then on the right-hand side, you have the application domains. An example here is our highlight programs, where we have an AI-driven design of materials highlight, which I, for example, coordinate together with Milika Todorovic from the University of Turku. We are very active in building collaborations in Finland and abroad. We actively work with also other Research Council of Finland flagships, for example, the FinCERES Materials Cluster. Then also key research partners from abroad, many different kind of companies in Finland and internationally, and then finally also the public sector. What I want to highlight in this slide is actually our collaboration with the European, with the ELLIS network in Europe, which is actually key at the moment because we are working very hard to establish an ELLIS Institute in Helsinki. So ELLIS stands for the European Laboratory for Learning and Intelligence Systems, which is actually a pan-European network of units and institutes that focus on AI excellence in Europe. A couple of these units have expanded to institutes in Europe. The first one was Tübingen in 2023, and now the second one will hopefully be established in Helsinki in the years to come. We're now actually on the ramping phase and hope to get full operation in 2032. I just wanted to quickly mention this because I think it provides a lot of benefits for different kinds of actors in Finland and also in Europe. And you can actually just find more information in the FCAI website given there on the slide. My background is partly in chemometrics, and I just want to provide a quick historical context for the idea of design of experiments and using AI and machine learning for the topic. Design of experiments is actually an established methodology in the traditional statistics and chemometrics field. We generally have two different objectives. One, on the left-hand side of this slide, we might be interested in mathematically quantifying and comparing the effects of different factors, here meaning experimental conditions on our measurements. These ideas were first laid down actually by Fisher already after the First World War. We normally focus on just a couple of different levels per variable, and the research is often more fundamental, and it might be difficult to describe a clear mathematical objective. And then the second objective on the right-hand side is optimization. This was actually something that was originally started when chemists started working with statisticians in the 1950s. In the traditional DOE methodology, we normally use linear and deterministic quadratic functions with, say, 3 or more levels per variable. The focus is, by definition, more applied, and it's easy to mold it into a mathematically defined objective. Now, this optimization part, we can nowadays then replace with AI, which is one of the core topics also of this webinar. And with these words, I would like to hand it over to Arto Klami. Arto, please, the floor is yours.
Thank you, Mikko. I need to get my presentation started. Okay. Good afternoon, everyone. So like Mikko introduced, I'm Arto. I'm a professor at the University of Helsinki and at FCAI. I'm both going to give a general overview on how we can do design of experiments in an active manner, and then also talk much more about things that go even beyond that. So how can we actually help people with AI technologies in all kinds of scientific discovery problems? I'm going to be not showing any equations. I'm trying to remain on a very general level. So I'm talking about the latter setting that Mikko explained, so the kind of optimization type of problems. So we're studying an iterative research process where we're trying to find, let's say, the best possible reaction for synthesizing a particular chemical or a materials discovery problem, or more generally, something that steps far outside of these kind of natural science environments. And we could, for example, be talking about how to reduce traffic incidents by putting more traffic lights or changing speed limits or any other policy changes. And we're talking about an iterative framework where we do this, so we can always carry out an experiment and then make conclusions based on that, and we keep on repeating this. And now the idea is, I'm studying the general question. So what's the best possible use of machine learning or AI in this context? And let's say more generally, what are the alternative ways of what we can do? I'm starting with a very brief background on how does this relate to this kind of classical design of experiments. So from my limited perspective, design of experiments is in general so essentially so that you in advance figure out that, okay, I'm willing to be able to make N experiments, N is maybe 20, 30. You figure out all the experiments you're going to run, then you make all the experiments, and given that, you try to find an answer to your solution. So you maybe build a model afterwards and figure out what's the best possible configuration you could see. In my notation, X is always something that the person can decide, and F is the unknown process that we want to somehow understand. When I talk about iterative experimentation, I mean any process where we make a measurement, then we observe the outcome of that measurement, and based on that information, we decide what's going to be the next experiment we carry. I'm stressing this simply because from a philosophical perspective, this can never hurt. We can always ignore the outcome of the experiment if we so choose and stick to a predetermined design of experiments. But formally, there is some information in the outcome, and we should be using it. Of course, in practice, if we do this poorly, let's say a human researcher just randomly guesses, next time I'm going to do this, it's going to be worse. So that's like more like a theoretical perspective to when should we be doing this. And what I'm talking about is, let's try to formalize this process a bit, thinking about this iterative optimization as some sort of a workflow. There's a very simplified figure on the left where we can either make a measurement, and then after each measurement, we need to choose what is the next measurement we make. And I want to put it like this, because I want to turn the attention to the decision that's going to happen here. What's the next experiment? It could be done by a human. Simply a researcher figures out what I'm going to do. It could be done by an algorithm, and it is going to be in many of these automated solutions. I'm arguing that in most cases it should be done by the two together in some sort of human AI collaboration. And I'll be talking about different ways of doing that. And for making these optimal decisions, we always kind of need to know everything that's been done until now, all the configurations we evaluated, all the experimental results we got, and also, let's say, in an ideal world, also some sort of domain knowledge. So what do we know about the system? So what does the researcher know? I'll start by giving a very quick overview of Bayesian optimization as the standard automatic way of doing this. I know that Morten and Søren are both going to talk something about this, but that's like just simply an example. So we have here on the right some unknown function that we would want to find the maximum value of that, which is more or less somewhere around here. And we've already made a few measurements. Now the question is, what should we be doing next? The basic idea is that let's fit a model to whatever we already measured. We can fit some sort of a function here that interpolates between the points. Let's not go into details on how I did it here. That's not quite enough. That's not really telling us what's the next optimal thing to do, but rather we would want to somehow quantify the uncertainty. Close to the measurements that we already made, we know the function quite well. Further away from those, we don't. And now, given this information, so the uncertainty and the current best model, those are like the sufficient necessary information that we need to make rational decisions on what to do next. This can be quantified by defining so-called acquisition function, a function that uses the uncertainty and the function value to pick up a solution that's hopefully good. So it could either be we are exploiting the knowledge that we already have, or we are exploring. We are trying to find some place where there is possibly a good solution. And I've already marked here that what's the next configuration we're going to evaluate. And once we do it, we observe that no, that wasn't actually a very good solution. After that, we go back to the beginning. We update our model, we update our uncertainty estimates, we figure out what's the next good point to choose, and we just keep on repeating this. So once we've done it for a few rounds, we figured out that yes, the optimum is somewhere around here. We don't know the function everywhere. We've only been kind of exploring it in the areas that matter for our problem. And this is usually tends to be a much more efficient way of using the data than, let's say, a predefined grid over this whole space. This is just the background of how do we usually do this if we're doing it in an automated way. I want to talk about something else. Before that, I just want to remind that there's nothing here that relates to what is the particular optimization problem we're worrying. This is a general purpose algorithm. You usually would want to put some domain knowledge into the question of how do I estimate how the function works, but nothing else. Much more interesting scenarios are things that where we don't just have one way of inspecting our object of interest. Maybe we can evaluate it in multiple ways. Let's say if it's a chemical reaction, we could ask one of 5 different chemists to carry out the reaction. They're not going to get the exact same result. They have their personal styles on doing it. Or we could be having, besides the experimental device, a computational simulation that tries to model theoretically what would happen for this particular sample, or we could have a machine learning proxy that predicts the outcome. And this is just a general template of the kind of an optimization problem we could have, where we now need to make 2 decisions. What's the configuration to evaluate? And which of the evaluation machines we use. Ideally, we make them jointly, we could do them separately, but that's simply a way of kind of framing these problems. Luckily, we already have existing good algorithms for handling these kind of situations as well. A very typical scenario in this kind of a setting is so-called multified fidelity Bayesian optimization. We have different ways of evaluating the same function, usually so that some of them are costly and slow and accurate. That would be meaning carrying out the actual experiment, whereas some of them can be ridiculously fast. A machine learning proxy that only takes milliseconds to evaluate, but they are noisy. We don't know whether they are actually modeling the function well. I'm not going to talk about the algorithms. They exist. and usually they would find the kind of intuitively natural solution. We should keep on querying these noisy but fast measurements much more often, and then we eventually get to confirm the results with the costly real experiment. An important side observation that's what's happening here is that if one of this fast system was a machine learning model for trying to estimate what's happening, we're actually getting for free information for updating that model. We're getting one observation every time we evaluate the function for real. Now, one of the main claims that I want to say today, that what I want you to remember, is that actually every optimization problem in the world is exactly like this. We always have some alternative ways of evaluating the unknown object. In particular, we have the researcher. You could ask a chemist, if the reaction is going to be done in these conditions, will it work? They will always have an answer. It may be a bad answer, it may be a good answer, but it's always there. So we always have the option of asking the researcher, and we should be thinking about the system so that it's included there. We just usually don't do so. You could also always have a predictive machine learning model that's initially ridiculously bad. You maybe trained it based on 4 examples. But over time, if you think about it from this perspective, you will be getting more and more data to actually start making more useful predictive models. And more generally, so that's one example of what's the role of the user in this automated era of solving these problems. And I'm just going to make a just general statement. We should not ignore the user. We should not ignore the researcher. And within this same interaction pattern, where a researcher just goes and carries out experiments, there's numerous ways of how we can use the information. The basic thing, you would usually should allow the researcher to recheck the recommendation. I'm not going to run this experiment. I already know it's going to be bad, or it's going to break my device or anything. I'm not going to do it. But you can do much more. You could think about giving n different alternatives for a human researcher who selects one of them. The model will learn something about why the user picked it. Or you could vice versa, the human could be giving suggestions and an AI selects from those. Or as in the previous slide, of course, we can always just ask the researcher, using the researcher as a passive information source within this optimization. To give a concrete example of what this would mean in practice, this is a work from Aalto University 2 years ago. Human in the loop optimization process. This is for discovery of new drug molecules. So we already have these generative AI methods that can create synthetics, generate new types of molecules, which are not usually creating very useful molecules most of the time. You can guide these models by giving them so-called reward functions that indicate what kind of molecules you would want to ski, but specifying that function in advance is very difficult. So we can do this kind of human in the loop processes where we have an outer loop where we just generate more and more molecules. And then we have an inner loop where we take an already generated set of molecules and iteratively do essentially active design of experiment within that set, selecting one of them to be shown for an expert who analyzes it however they want to, and then indicates whether this is good or bad. And then we collect this data and use it to learn a better model of what kind of molecules we want. And then we go and generate, again, a new set of imaginary molecules. And we just keep on doing this kind of a loop where the human is in an integral role, implicitly guiding the model in cases where they can't do it explicitly. Another example of what we can do in this same interaction pattern is actually try to learn what humans know about these systems. Let's have a human solving the problem without any assistance from any sort of an AI. They always just decide what to do next. Then we passively monitor and observe what they are doing. And suddenly our learning goal is, let's figure out why they did it. So we want to understand, maybe they have a bias. They always avoid exploring certain parameters and so on. We would want to tell it for the user. We've done some work on this where we explicitly model the user's behavior as if they were a person carrying out a Bayesian optimization, and then solve an inverse problem that given the decisions they made, what they needed to assume about the function. So for example here, if the user ended up only exploring this area, it can be interpreted as having a very strong prior that it's simply impossible for the optimal solution to be somewhere far away. Otherwise, they would have needed to go there and verify. More generally, so what I'm interested is in working towards much more general AI assistance for these kinds of systems. We can always split the world. So there is a user who interacts with the environment, makes experiments, and then there's AI who interacts with the user, makes recommendations, observes what the results were, and most of the time these algorithms should be building explicit models of what the user wants, either the reward function in the drug discovery case or the explicit model of a human search as Bayesian optimization with unknown priors in the other example. Where we want to go is actually have AI that assists in making these decisions in much more complex environments, not just within one iterational system, but in a system where you take one sample, you pick which sample you analyze with which machine, whatever the outcome is, you decide either I need to go and analyze this in a further machine or I need to do something else. And in any AI that does anything useful here, most of the time needs to build an internal model of what the user wants. And it, of course, needs to keep updating the models of how the world works. So the proxy models for these unknown functions. It interacts with the researchers in many arbitrary ways. It can use the researcher interaction in many ways, but the main goal is to help them make the decisions. And usually we like the research to remain in charge. So I don't want to automate scientific discovery. Unfortunately, I can't give you a solution for this. We don't have anything like this. And the reason is that we don't know how to create them. We don't have any sort of environments that would expose for AI researchers that what's needed in a real research case. We don't have data for training these kind of things. And even if I had a great algorithm, it would be extremely difficult to take it into use in any environment. We are still working on solving this thing. So we introduced this idea of a virtual laboratory, a kind of a concept that is designed specifically to isolate the decisions, the parts where AI can do something to help the researcher from everything that's specific to the domain. Whether it's chemistry or traffic planning, there's components, there's models. We don't really care about what they are. We want to focus on the decisions. We're working. There's a link to this vision paper where we outline the idea of how will the world change once we have these kind of environments. We're also working on proof of concept software that essentially gives a unified language for describing research processes, starting from the standard Bayesian optimization type of loops to arbitrarily complex collections of decisions in a lab environment, designed specifically to isolate the domain-specific components from the decisions where an AI can help, essentially becomes a workflow manager software that has this agent-based architecture where it can call AI agents to make these decisions or help making them, and is intended exactly as the platform where we can then develop and benchmark, evaluate different kind of algorithms in diverse research conditions. So to conclude my talk, I started by saying that whenever we do iterative optimization, we need to be doing it actively, always looking at what we've already done until now. Bayesian optimization is a very good solution for this. It's already broadly in use, and we'll hear more about that soon. I wanted to point out that there is so much more to Bayesian optimization than the standard case. We can always learn how to use machine learning proxies within those, how to ask users. I would always want to see the user to be in some sort of a role there, and there's different roles they can have, which usually mean also models for how the user behaves. And then I'm advocating for this virtual laboratory concept, helping us to change the way we work. Stop working on isolated decisions in isolated field-specific techniques and start working on general AI assistance which we can do when we have the right language and right software background for that. Thank you.
Thank you very much, Arto, for your presentation. I think the topic of your talk really hits to the core of even the current discussion when we think about using machine learning for material and process development in general, which is my field, because we often sort of have this disconnect between domain knowledge and a fully data-driven approach, right? So especially chemists traditionally are very worried about, okay, if we start using data-driven methods, like the ones that we're going to hear more about in this seminar, what happens to domain knowledge? What happens with the existing experience that a lot of, especially people that have been working in organizations for a longer period of time, how do we include that information into the decision making? I think this really hits to the core of that. How would you comment that, sort of taking in existing domain knowledge from people in organizations that have worked there for decades and combining that into a data-driven approach?
Yeah, I fully agree. That's one of the main goals here. So I have a concrete project, for example, exactly in pharmaceutical chemistry, where the basic thing is that we know for sure that every chemist has a deep understanding of what's happening. They have a lot of their kind of personalized intuitions of what could work here. But you can't really write them down. So we need to think about their expertise somewhere embedded into these systems that have some sort of an AI components. We can't ask them to kind of specify exactly what you know, and then we give it for an algorithm to digest. And most of the cases, the usual kind of the interface perspective for this is that it's a discourse, it's discussion between AI and human. It could be natural language, or it could be in form of selecting alternative candidates, but they need to be there to kind of answering exactly the questions that they know the answer for.
I'm going to ask another question because I think this is very interesting. So if we think about the design of experiments, whether traditional or BO-driven, I mean, using machine learning for the same purpose, we often use these tools for purposes where we don't actually have exact closed form chemical or physical equations to describe whatever process, right? So then we take a data-driven approach that we assume that incorporates all the empirical uncertainties into the model that can come from uncertainties in the experiments, in the measurements, and so forth. But in this case, what you were talking about, would it be possible then if we would have some physical known equations, sort of some first principles equations that we could then sort of build into the approach? Because I know this is also something that a lot of people are thinking about. Why not use first principles models in the first place? Well, they don't always exist, but maybe this could offer us an alternative to use some of that information.
Yeah, I think that's exactly why I emphasize this prototypical pattern, that you can make your measurement, or you can have a first principles model or any sort of a computational model for how this is going to work. It can be, the basic idea is that it can be bad. We don't need to require that we have a full description. We just get some sort of an insights that this is physically implausible that in this condition this reaction could work or something. And this kind of we can embed it within BO in a justified manner so that we get theoretical guarantees or like proper algorithm decisions on how much should I then rely on this. And then the other thing is, of course, that also within these proxy models that we are building based on the measurements, then of course there you could also do like physics-informed neural networks or something as the model that you build from the measurements. So there's kind of two places where you can start adding more domain knowledge, and I do believe it's a key. I mean, we want to use as much of it as we can.
Okay, thanks, Arto. We have a question in the Q&A, so if you wouldn't mind checking that afterwards, and now we have to move on forward in the program. And for the next speaker, I would like to introduce Morten Bormann Nielsen. He works as a product manager in the Danish Technological Institute. Morten's going to talk about the Brownie Bee program, and I have to admit that I've been pretty fascinated about this ever since I stumped into it a couple of years ago. So really, Morten, please go ahead with your presentation.
Well, thank you very much, and hello everyone. I'll jump right into it. I just need to click here. So yeah, as said, my name is Morten. I am from the Danish Technological Institute. We are we are actually exactly the Danish equivalent of VTT. So we are similarly a self-owned company, and our primary goal is to sort of increase competitiveness of companies by implementing technology. And I should really emphasize that it's this implementation of technology that we work with. And what I will be talking about today is a tool that sort of makes it easy to implement a given technology. In this specific context, the AI technology of Bayesian optimization. So what has already been introduced, I will focus on a very simple problem to state, which is to find optimal settings for a process based on a set of predetermined quality requirements. So this optimization of something that Arthur already spoke about. There are many ways of solving that problem, but one effective way is, and what we're focusing on today, is Bayesian optimization. And Bayesian optimization is just a mathematical technology that lives inside this software tool I'll be talking about called Brownie Bee. I should stress that in most of industry, even though Arthur showed very well that design of experiments is basically 100 years old by now, most of industry across the world does not use it. What is the typical status at many companies, particularly small and medium-sized companies in our experience, is that they use one factor at a time optimization, which is an extremely ineffective way of solving this problem of finding optimal conditions. And it's probably because we're taught this already in basic school as part of sort of the science classes, and it's in many cases never really sort of walked back upon or challenged even through high education. And in this approach, we might have a process that we think might depend on time and temperature. And a typical chemist, such as myself, I'm a chemist by training, would often go out into their lab in an R&D environment and select a fixed time and then run a temperature series and see that quality is best here. And then they would sit on that temperature, run a series of time points, gather data, and see that the optimal condition is here. And this is extremely ineffective for anything that is moderately complicated, simply because there's no guarantee that you will find an optimal solution, even when it exists within this playing field that your factors are sort of defining. And it becomes sort of very confusing and complicated to keep track of what you have tested if you just do this in an Excel sheet or on a piece of paper, which is, again, what most of industry does today. As Arthur also mentioned, classical DOE was sort of invented to try and take the approach that if you want to figure out how a process behaves, you should draw a map of that process and use it to find your way to the goal. So in classical DOE, you would typically choose a bunch of experiments up front in this way, designed to draw the map of the process or the product performance. So these 9 data points would be used to draw this landscape, so we can use the landscape to predict that this is where the solution is. And in principle, this approach is a much more sensible way of attacking this problem than the approach here on the left. But in very, very many practical realities in many companies, the amount of experiments it requires you to do in order to draw a realistic or useful map of a complicated problem becomes very, very large or practically intractable in many contexts. So this is where Bayesian optimization sort of comes into its own right and provides a much more, you could say, appetizing alternative to classical design of experiments. As Arthur showed, at its core, Bayesian optimization starts out collecting data at a few points in your sort of possible solution space, and then it draws a model or a landscape, as I like to call them, that we know is very wrong, but that landscape still contains some information that allows us to calculate where should we do the next experiment. In my animation here, I've sort of highlighted it as a yellow color. So you could think of it as, of all the possible settings I could choose here, the more yellow, the more productive it is to run an experiment in those conditions. And the Bayesian workflow is simply to then go to these conditions, gather data, redraw the map, ask for a new set of settings, and so on in an iterative fashion until your landscape stops changing or you find a solution that's good enough. And on the whole, you could say that the algorithm here in Bayesian optimization is really designed or appropriate for the case where it's the solution that is important. Basically, you need to find the right recipe as fast as possible, and you don't care about all the recipes that are bad. In the DOE, classical DOE framework, that is really appropriate when it is the map itself, so the model or the full description or the full understanding of how the factors interact with each other. When that is important, then DOE is still a really good method. But from the vast majority of companies, this is much more aligned with their project goals or their development goals in many cases. So let me just sort of try and qualify this further and show the strengths of Bayesian optimization with a concrete example of something that classical DOE is hopeless at solving. And that involves a complicated chemical reaction such as the PCR reaction. So this is the kind of stuff that happens inside COVID tests to sort of amplify the DNA of when you check for COVID. So something like a PCR reaction has a bunch of settings that we could change in order to optimize the quality of this chemical reaction. So in this case, quality is maybe the effective yield. So the yield times the purity, for instance. And if you were to attack this problem with classical DOE, it's really not very appealing, or it's very, it requires a lot of work to do, because you would typically start out trying to eliminate some of the factors by what's called a screening experiment, and then you would try to draw the map in the using the factors that are active or that you see are relevant for quality, which in this particular example would require almost 100 experiments on its own. And for a problem of this complexity, you would therefore, in a very optimistic case where I am assuming very good data quality, need to run something like 120 to 160, maybe 200 experiments just to figure out whether there is a solution to be found anywhere. And to make matters worse, when we are working on a process where we don't have a lot of domain knowledge, classical DOE tends to favor looking in the corners at the extremes to sort of highlight the differences that different factors make. But when we don't know processes very well, the corners might not even work at all and give very uninformative data. And this is one of the sort of practical reasons why classical DOE is underutilized in many company contexts. That is sort of the mathematical argument. The other argument for why many data-driven techniques are not really used much in industry has to do with humans. So most scientists to this day in many companies still think that one factor at a time is the right strategy. And they're very confident in that belief. So when we, in my institution, go out into companies and try to teach them to do something different, we have to kick them off this mount one factor at a time and teach them something slightly more about designing experiments. But then if we try to teach them classical DOE, they get really scared by how many experiments you have to run. They might not really know how good their data is and how their measurement systems work. Or even worse, they might not have an objective measurement system. They might just gauge quality by looking at it. And in many cases, particularly if classical DOE is introduced to a company, they will say, I don't want a map of my process. I just want to find a good recipe. So I like to call this region, when you try to teach people to use something better than one factor at a time, the valley of despair. And it would be nice if something existed that was able to drag these people across the valley of despair in a simple way, so they could at least get started doing something that is better than one factor at a time. And this is what Brownie B is designed to do. So let me again now apply sort of the same, or take the same problem and show you what Bayesian optimization would do here. So with Bayesian optimization, we still have this PCR reaction with lots of things we can control. And we would start out just like in classical DOE to define factors that we would change. And then we would go out and do a limited number of experiments to begin with. So in this case, we want to increase the yield of this reaction. So we pick 15 initial very different ways of running this experiment and gather data here. And these are then the results in this example. So the empty circles is where we got complete flatline response, no signal at all. And the blue circles is where the signal is in some cases very low but detectable, and something above zero. So basically all of these reactions worked really poorly, but they didn't work equally poorly, all of them. And since they were, created with different settings, there is some information here that could potentially allow us to choose a new set of experiments that might yield a better result. So this is what Bayesian optimization does, is it just incorporates each result as it comes in, chooses a new set of settings in an iterative fashion, constantly refining its guesses until we, in this case, we reach our result. Now, maybe this was good that this was what we had the budget for, but in some cases we might also wish to continue and with us, because now we found what we wanted to get to, 500, and maybe we're curious about whether we have plateaued. So I'm just going to sort of bump the goal up to 1,000 and continue for a number of iterations for this particular problem. And in this case, after 35 runs, we have far exceeded the initial goal on a system that is extremely complicated. And again, I showed you for comparison, DOE to even get started on this would require, on the order of 5 to 6 times more experiments to run to make any headway on this problem. Right. That's just to sort of show you the kind of complexity where Bayesian optimization really shines. But in order to make it easy, we have built a tool that sort of abstracts away the math that's happening and simply guides you towards how to pick your experiment. And we've built this in a browser in a collaboration together with Novo Nordisk, where that Søren is from, and he'll be talking about that in a second. So let me just change and show you live what this looks like. So Brownie B lives on the website brownieb.io, where I have the unfortunate fate of being the face of teaching people how to use it there as well. But you can try it out for free on this website and simply by registering. I have already registered, so I'm just going to log in. And just to show you how the process works, we're going to create a small experiment. So when I press this create button, it creates a new project for us, and we'll call it FCAI webinar. And we can add a couple of factors. So maybe we are interested in baking a cake or something like that. And we'll need to add some flour to our recipe that we might want to change between 200 and 500 grams. We might want to add some sugar between 50 and 150 grams. And we might want to use eggs in our recipe between 0 and 3 whole eggs. And since I don't want to break eggs apart, I want to only get suggestions with whole numbers. And then maybe we want to add some food color to our dough or something like that, because if it's for a birthday cake for a kid or something like that in this example. So I'm just going to go with red and blue. And you can see here that this is basically where I add our factors one at a time with the limits. And as I've done this, Brownie B has begun suggesting a set of these initial experiments that it would like us to go out and do in order to get started. And as we scale up the system, Brownie B will suggest more and more experiments to get started, because you need a certain minimum amount of information before the algorithm can really work. But once we're ready to start experimenting, we'll transfer them down here. And then it's off to the kitchen or to the lab to carry out your experiments. Now, Brownie B expects you to tell it about the system you're trying to optimize by telling it about the quality you observe. And in this system, quality is a fixed scale between 0 and 5, just to make it intuitive, that obviously want to reach 5 stars, if you will. So you have to use this tool, you have to be explicit about your goal and how you want to map it to this scale of between 0 and 5. And in this short webinar, I'm not going to talk much about how that is done in practice. There's a couple of videos on that on the Brownie B website that you can look into. But for now, let's just imagine that we are just talking about a cake quality, that we are asking people to just give it a rating between 0 and 5 stars. So now I'm just going to make up some data in this case. You can use the drop down here, or you could also simply type in the numbers and add them as you go. But now for this, it's just a bit quicker. So now once I've gathered results for these initial experiments, where we use a low number of those, Brownie B will then actually begin building a model for the system. I'm just going to ask it for one next experiment. And based on the results that we've seen so far, Brownie B is now using this Bayesian optimization algorithm to suggest a new experiment or a new recipe to go out and do in order to improve quality further towards a goal of 5 stars. And beneath our suggestion for the next experiment, it is also showing us its present best guess at the optimal recipe. So I've just made up this data, so this might not make sense at all. But basically, it's showing that it wants us to use about 410 grams of flour, no eggs, and the blue color. It knows the system. It thinks it has information close to this recipe, but where we don't have any data, the uncertainty is huge, because this is already a moderately complicated problem, and we don't have a lot of data. Finally, here at the end, we have a histogram of what Brownie B expects the quality to look like if you keep producing at this recipe. So in this case, at this stage, it expects the quality to be between 4.2 and 4.7 if we just kept producing cake with the recipe that is shown in the predicted best solution. I just want to go out and show you just a bigger system. This is the PCR reaction example I showed you from before, just to show you what it looks like if you add a lot of factors with a moderate number of experiments here. And in this case, the process is a bit further along, and we can use these graphs to, for instance, see here that the denaturization temperature is best set to its maximum value, and if we reduce it, the quality is going to drop off. We don't know how bad it's going to be at the lowest temperature. We just have enough information to conclude that it will be bad. And on the other hand, the denaturation time, we're not very sensitive to, because the dependency on quality compared to this factor is actually pretty flat, as an example. All right. Since this is a short webinar, I'm not going to dive into a lot more detail about this, but instead jump back into the PowerPoint and just continue with a few last points about this. So we have built Brownie B and designed the interface through implementation. So there's a bunch of small and medium-sized companies here in Denmark that have been using Brownie B on problems that they were working on and provided feedback to make it more usable for people who don't have a data science background. And we've gotten it now to the point where, I've shown you the interface. It can be run by a kid, and I test it on my 8-year-old son from time to time, and it works quite well. But just to show you that applying this in the real world is something we have extensive experience with, and in some cases, for instance, in the company Vestas Aircoil, who produce coolers for ship engines, it significantly speeded up their sort of the pace with which they can develop a new solution when there's a customer request. Instead of is a process that normally takes 2 years for them, but using Bayesian optimization, they were able to produce a new product using a complexity that they normally do in 3 months instead. You can read more about all these cases on the website too. So instead, I want to sort of highlight with 3 last points, just requirements and common pitfalls you should be aware of when you work with Bayesian optimization in the real world, and not just using Brownie B, but it applies to Brownie B as well. And I really want to state that Brownie B makes it easy to use a good method. And the inner side of Brownie B is really about the right side of this figure, which is about how you choose the next experiment. You obviously carry it out and rate your quality and then update your model and use it to pick a next experiment. But very critical to this method is the first initial steps, which are not part of Brownie B as such. So I want to sort of highlight those, which you should be aware of there. So the first pitfall is about clearly defined goal. And many companies suffer from not having clearly defined goals, and therefore they commit errors of the third kind, which is the error you get when a specialist goes into the lab and produces a perfectly correct result to a different question than what their manager was asking them. And it is very important when using data-driven approaches that you are actually very clear about sort of the improvement that you're looking for, how many runs you can expect to get, and you have to consider these things and make them very explicit to make good use of data-driven tools. The second pitfall is this measurement of quality, so the response we get and the quality we tell a program like Brownie B, because it's still a data-driven technique which suffers from the CISO principle, which is shit in, shit out. So if you give it unreliable data, it's going to give you unreliable suggestions. And sort of being very explicit about how you measure quality is a very important part of using these tools. This is also why we force people to use a 1 number for quality in Brownie B, because it forces them to talk about how they want to translate their practical context to a number, which is often very valuable in and of itself. And the last point I want to make is about how we choose factors with domain knowledge. And I want to quote Douglas Montgomery, who's a very big figure within classical design of experiments. And one of his theorems is that you should never let one person design and conduct an experiment alone, particularly if that person is an expert in the field of study. And this sounds completely insane, but I want to sort of highlight a reason why this is particularly true in industry. And I really like, Nico, that you asked the question about domain knowledge and making use of that. And it's actually, in my experience, very dangerous to do, or at least to over-rely on. Because in this example here, we have a process that's running at these settings. And we have a very experienced colleague who has been in the company for 30 years. And we have suggested that we should try and change temperature and time to improve the quality compared to the present setting. But this employee is very adamant that we can't improve quality further in this system, and we have tried temperature and time many times. So it's a stupid exercise to even try changing the system, according to our experienced colleague. Now, if we went out and repeated what this employee has done and changed the temperature, we actually see that changing temperature decreases quality. And if we change time in the way that our colleague has done so, quality also doesn't improve. So in principle, our colleague here is not wrong, or they have actually a good reason to say what they're saying. But as people who know classical design of experiments or are used to data-driven techniques will know, what they've missed by working with one factor at a time is that these things are synergistic. So you have to change both temperature and time to get a good result. And this is, in my world, one of the biggest dangers of relying on domain knowledge when trying to predict the outcome of experiments, is that quite often in environments where people have never used a data-driven technique for optimizing, they've actually learned the wrong lessons. So their domain knowledge is incorrect or incomplete as a result of that, because all they have is these straight lines through parameter space. All right, I won't harp on further about that. I just want to highlight that there's a bunch of companies already using Brownie B across the Danish industry, and maybe you want to give it a try too. it's designed to make it easy to get started with finding optimal settings for processes based on a set of predetermined quality requirements. And here's the website information. And I should say that the underlying math is open source and still being actively developed as a collaboration between ourselves and Søren from Novo Nordisk. And with that, I'll open up for questions and comments.
Thank you very much, Morten. This is fascinating. I really love the quotes that you have gathered there, and it's really an impressive list of real world companies that you've worked with. I'm going to take a step back and talk a bit about the differences of traditional DOE and also Bayesian optimization, and I'll also grab a couple of questions that participants to the webinar had submitted beforehand. Mm-hmm. So basically, there's two main advantages that are pretty transparent on using BO, right? You might be able to describe more complicated functions, right? So the response surface or the landscape is more complicated, or possibly more complicated than it could be with traditional DOE. Mm-hmm. And then you can do it quicker, right? So you're able to find an optimum with a lower number of experiments. Okay, but how about the downsides? I mean, explainability and interpretability are mm-hmm. sort of often key topics when we talk about, or when we compare machine learning methods with more traditional approaches. How do you comment on that? How can we ensure that the results and recommendations are transparent and understandable?
Yeah. So basically, I wanna say that in order to be more effective with Bayesian optimization, what we're sacrificing is getting a good model everywhere in your space. So Bayesian optimization will tend to gather more data where quality is good and less data where it is bad. And that means that your model will be much less reliable in areas of medium to low quality. And that will, in some cases, result in less explainability. And if that is very important to you, like full explainability, obviously you have to build a reliable model, right? So that's the downside. But in many practical realities, you don't have time to build a reliable model, or the problem is too complicated. Or in some cases, once you find a solution, then you might want to do classical DOE close to the solution to build a reliable map there that you can use to sort of gauge or document process stability, or register your process with authorities if that's what you need to do. But in practice, it's not very productive to draw a very reliable map of a process that produces horrible cake if you are in the business of selling good cake. So they supplement each other. I'm not advocating that you should only use one or the other.
One thing that I'm really fascinated about the Brownie-Brie approach is that it really sort of makes it easier to use a systematic approach without specialized statistical training. And you mentioned that you had experience on working with a lot of different companies. What's your impression of sort of the user experience? So the experience of companies using this method mm-hmm. compared to whatever alternative that they'd used before?
I think on the whole, our experience is that it works really well, and people really like it, because the unintended side effect of implementing something like Brownie-Brie is that all of a sudden it is very easy to figure out based on your data what to do next, and people typically have that as the main barrier for using the something data-driven right now. But then immediately after that, it becomes obvious if you haven't had the important conversation about how do we actually measure quality and what is our goal in terms of quality? How much better should it become in order for us to really care about it? Most companies, they don't do that, but they are unaware that they don't do that. And it's very hard for me to convince them that they're not very good at specifying their goals or talking about their quality. But you can persuade them that statistics is difficult and they should use something like Brownie-Brie. Then once they do that, they immediately figure out that they are bad at the other stuff, but they just haven't been aware of it previously. And then it's typically not very difficult to fix, but this tool actually forces you to work in a productive way as well, and that's very much by design.
Thanks, Morten. We have a couple of questions in the chat, but I think you're better equipped to providing good answers to those questions. So if you wouldn't mind, I would ask you to answer some of the questions while Søren is presenting. Thanks, Morten. And now we would move on to the webinar's last presentation. We are delighted to introduce Søren Furbo, who is a process optimization specialist at Novo Nordisk. And really, I have to say that I was delighted that Søren, you were kind enough to accept our invitation, and I'm really looking forward to your presentation. Please, Søren, go ahead.
Thank you. So, as mentioned, I work in Novo Nordisk, and I will talk about how we use Bayesian optimization to optimize physical processes. So what I hope you will get out of this presentation is, well, firstly, that Bayesian optimization works really well for certain types of physical processes. I'll come into what types of physical processes I mean when I say certain types. And I'll also specify that it actually gives you a lot of benefits. But also that you need to know the process you're optimizing. It's really essential that you include some domain knowledge, because you really need it. So I'll start by talking a bit about Novo Nordisk. Then I'll explain why Bayesian optimization is particularly good for certain kind of physical processes. Then I have two cases. I've worked on the first one, so I can go into a lot of detail there. The other I haven't worked on, but I can still explain something about it. And then I will conclude. So this is just a slide about Novo Nordisk. We are a pretty big company. I think we're up to 66,000 employees now. We make a lot of insulin and serve a lot of people. But the important thing I want to say about Novo Nordisk is this, that we are not just, we aim not just to be financially responsible to make money, that we need to keep producing medicine and keep developing medicine, but we also want to be socially responsible and environmentally responsible. And I'll come back to these 3 points at the end and explain a bit about how Bayesian optimization of physical processes help us with all 3. So why Bayesian optimization, or why does Bayesian optimization work well for physical processes? So physical processes, if you optimize something physical, it's typically characterized by it's slow. Actually testing a recipe takes somewhere between 10 minutes and a few weeks. It also requires expensive equipment. So each experiment costs a lot of money, or takes up a lot of time on expensive equipment. So the number of experiments you can actually do, you are allowed to do, is relatively low. And this is a place where Bayesian optimization really shines. It is eerily good at getting a lot of information out of a system from very few experiments. There's also the processes we typically look at are hard to parallelize. So if you have to use an expensive equipment with, say, a few people to make it run, you're not going to be allowed to have 10 of those running in parallel. And that also speaks to Bayesian optimization, because Bayesian optimization, it's really good at suggesting the next experiment. We can kind of make it work to suggest a few experiments, but once you get beyond that, it starts to get really hard to get good suggestions out of Bayesian optimization. So if you want suggestions for 10 or 50 or 100 experiments, Bayesian optimization might not be the best suggestion for that. And also physical experimentation, it's typically so complicated that you can't make mathematical solutions. So you can't do any of the mathematical approaches we have to optimize processes. So all of this sums up to that if you have physical experiments where the first 2 points hold, then Bayesian optimization is a really good fit for optimizing it. So we'll go into the first case where we are trying to optimize HPLC methods. I should probably start with explaining a little bit about HPLC. I imagine many of you don't know what it is. So we have a sample that contains several compounds, and we want to know something about those compounds. Which compounds are in there, how much is in there. We can't measure directly on the sample because the different compounds will interfere with each other. So we can't get an accurate measurement when they are mixed. So what HPLC does, it separates the compounds in time. So each of these peaks is one compound, and now we can measure them independent of each other. So we can go to which compounds are in the sample and how much are there. This is an enormously important instrumental platform for Novo Nordisk. We have a lot of machines standing around running, and they produce a lot of results. So this is really something where if we can make this better, we can do a lot better as a company. But unfortunately, it isn't that easy to optimize. So the way it works is you have a steel column with, say, sand in. You pour in your sample, and the compounds stick to the sand, and then you pour something in. That's the eluent, and then the compounds exit or pass through the column in different times depending on their affinity to the sand. So you can choose different chemistries of the sand. You can choose different chemistries of the eluent you put in. You will typically also change how the composition of the eluent during the run, and then you have temperature and flow and a lot more. So we need something systematic. But the problem is that, each experiment takes a long time. So we can't do DOE on this because there's simply too many factors, and we end up with too many experiments needing to be done. And they're also hard to model. There are some methods to do it out there, but they typically also require a lot of experiments. So this all seems ideal for Bayesian optimization. Then we also need to choose the optimization target. We could go by how much chemicals we use. I mean, we want to limit our environmental impact, so that's good. The sample could be expensive, so we want to use as little of that as possible. That's typically not a concern for us, but it could be for others. But what we ended up with was time spent, because we want our analysis to run as quickly as possible so we can analyze as many samples as possible on the instrument. And then we combined two different measures of separation quality. So how many compounds can we separate and how well are they separated? So we optimized towards two targets. So what we built an app, because getting people to actually use the Python code behind it is not going to work. So we've built an app where the expert can put in, well, there's some settings about which machine to use, where the sample is, and so on. And then there are the things to optimize, which at presently is the gradient time. So we've parameterized the change in eluent during the run with one parameter, the flow rate and the temperature. We feed that into Process Optimizer, which suggests new methods. We push that to the software controlling our HPLCs. We run it, we get the data, we find the peaks there, evaluate it, feed it back to the optimizer, and and that then suggests new methods. So this can run by itself. It can run overnight and can run over the weekend. And then when the user comes back, they can look at the chromatograms we have, they can evaluate them, and they can select which methods to go on with. And this works. It's up and running. We have users, and it works really well to map out the space and find good parameters. The second case is closer to manufacturing, because this is again something that's important to us to manufacture peptides. That is our business. So we had this process. You can see it's a pretty complicated process where there's a lot of steps. It's pretty high value. The cost of product from one batch is around 2 million euro. So if we could optimize this even a little, we could save a lot of money. We decided to optimize this step because it is the least controlled step of the where chemistry actually happens. So we optimized the concentrations of chemicals here. We could also have optimized which chemicals to use. We chose not to in this example. We also optimized how long time it takes, what the temperature is, and the volume. So time and temperature, at least, they're going to be a trade-off, because you want long time enough and high enough temperature that the chemistry actually happens, but not so long time and high temperature that you start making side products. So this is going to be a complicated optimization. We ran the optimization, and we did get very impressive results. It's a lot, and we made it a lot faster than we could have done otherwise. We also got a lot more understanding about the processes, probably mostly because we did something systematic, which and not one factor at a time, but we did gain a lot of knowledge of the process. And finally, we got a higher purity product, which saves us 10% of the 2 million, so that's around 200,000 euro. But also because it's purer, the later processes are simpler and use less resources. So it's also more environmentally friendly, the process we got out of this. So to conclude, as I said at the start, we have free responsibility. So Bayesian optimization of physical processes, it saves us money, and it allows us to do stuff faster, which, processes, projects moving along faster is also financially good. It also, whenever we do processes faster, it allows us to reach more patients faster. But also, we help with developing Process Optimizer as open source. So I would say that also talks into our social responsibility. And faster and better processes are more environmentally friendly. So it helps us with all three parts of our triple bottom line. I hope I have showed you that Bayesian optimization can work for physical processes. I hope I've also showed you which processes it's good for, and what I mean by works well, and that you need domain knowledge. So where to go from here? Well, if you would like to get started with Bayesian optimization, and of course you want, it's a really cool technique. The question is, do you code Python? If you do, we have the Process Optimizer open sourced in GitHub. You can just install it with pip. If you don't, Brownie Bee is a really good tool for that. And with that, I would, that was my presentation.
Thank you very much, Soren. This is fascinating and inspiring. I've been telling the story at VTT now when you mentioned to me that you had, or I've been telling the story that you have 1,000 HPLC instruments, because I think it's so fascinating. When I used to work at the university, I think we had two, the old one and the new one. It sort of creates immediately appeal to your work. Yeah. We don't have any Q&A, but I have loads of questions. So if you don't mind, we could chat a bit. You mentioned objective functions, or basically the objectives that you use for the optimization. And in BO, we mold these into an objective function, which is the mathematical description of the objective. You had many alternatives. Would it be possible to somehow evaluate the differences in potential objective functions using simulations? So sort of running virtual experiments somehow based on existing data sets to try to understand how the formulation of the objective function might affect the optimization?
Yeah, but so it sounds like you are asking about how you could make one synthetic objective function out of the many objective functions. Is that correct?
Yeah, how we could combine these different objectives into an objective function.
I would recommend you don't do that. I've never really seen it work well, that you take very different objectives and try to weigh them and add them or do whatever, because it takes too much knowledge that you don't have beforehand. So what Process Optimizer supports is multi-objective. So you add, you have multiple objectives. We use 2. And then it tries to map out. In our case, it's separation time and separation quality. So it tries to find the parameters where you can't get better separation quality without being slower. And then we have a discussion with the expert afterwards about what do we actually want. And so it serves the purpose that we don't have to sit down and try and find this combined objective function. But also, we can actually have the discussion with data. So we can show chromatographs and say, okay, so if you're okay with spending 13 minutes, you can get this separation. But if that's not good enough, then if you take like 5 minutes more, you can get this separation. And that means we can actually have the discussion about how good separation do we need and how long time can we afford to do. And you couldn't have that if you had made a combined objective function. So at least if they're very different, I think Morten has the typical example of price and quality. I would recommend that you don't combine them. I would recommend that you try to find the Pareto front, so the one where you can't make one better without sacrificing the other, and then have the discussion afterwards.
I think Morten has his hand up. Please, Morten, join the discussion.
Yeah, so I mean, it's one of the very first things that people ask when they begin working with Bayesian optimization, because I don't think any of us have really highlighted that most algorithms in Bayesian optimization and where most development has been happening has been with optimizing one number. And then there are some algorithms, as Søren said, for mapping the Pareto front in a productive way. That expands it to 2. But in many cases in industry, quality is many things, and it's inherently difficult. We typically try, and we have seen in some cases that. At least in an industry context, many things come down to money in the end. And if you can find and dig a little bit in the rest of the business, the context of how this process affects the final financial outcome, that is sometimes a productive way of combining several things about the process quality. Because in the end, in a company setting, at least, money per time is the one and only metric that matters in the end. And then whichever gives you the highest of that number will get you bonus points from management. But you know, if it is impossible for your organization to pick the trade-off in advance, then I mean, sometimes I just point at classical DOE and say, in classical DOE, you can measure all your 10 quality factors and draw the map for all of them, and then sit and have a talk about the trade-off at the end. But you can't do that for very complicated systems because the amount of work becomes too big. But if you're working with a manageable system in terms of the number of factors you're varying, then I still think that is a good approach to sort of picking the final or the right trade-off after the fact. But it requires a reliable model for that.
So Brownie B now houses. Oh, sorry. Please go, sir.
Yeah, and I will also say that, I mean, we did combine two. We did combine the number of peaks and the separation. So it's not that you can't do it. It's just if they become very far from each other, it becomes really artificial when you try to combine them.
And how have people at Novo taken up the idea of using Python for BO, or do you also use the Brownie B web interface? What has been the sort of on the ground?
We use both.
Feedback.
We use it depends on what people are comfortable with. So we have people who are comfortable with using Python, and they can use Process Optimizer in Python, and we have people who aren't, and we get Morten out to teach them to use Brownie B, and then we have that. So both approaches are good. And I mean, Brownie B it's a really good user interface. It really helps you. And of course, as any graphical user interface is bound to, there are limitations. So you can't do the multi-objective in Brownie B. And so it depends on the skill set or the skill level of the user.
Let's go in between the traditional DOE methodology and then the BO alternative. And Morten, please feel free to sort of jump in as well. So we're now talking about an alternative, but is there a halfway in between? Have you guys worked with examples where you sort of try to combine the methods, where you would have linear, deterministic, fully transparent methods combined then with nonlinear optimization somehow?
We have cases where it's also a discussion about, with the user about how many experiments can they do at a time. And again, if it's more than a couple, then BO tends to suffer. So if we are in the 5 to 10 scale, then we have had good experiences with doing something more classical DOE with most of them, and then do 2 points with BO, and that also works well.
Yeah, I also wanted to sort of say that, I mean, the way that Brownie B is set up and Process Optimizer by default as well, it chooses experiments to improve quality. So it tries to improve your metric. But in principle, there's nothing that prevents you from using Bayesian optimization in a way where the next experiment is placed where the model is least certain. If you did that as your strategy for choosing the next experiment, you end up doing what classical DOE does, in that you iteratively pick the point that would make your model most reliable with each data point added in an iterative fashion. So that's somewhere in between. I have yet to have a company that would prefer that above figuring out where the optimum location is as fast as possible. But in principle, there's lots of literature on it. It just changes how you choose the next experiment. It wouldn't need to change the modeling itself.
And the development of Process Optimizer, which is basically the back end of Brownie B. So that's the Python package. Was it somehow initiated as a cooperation between the two organizations that you guys work for, so DTI and Novo Nordisk? And who was the funder, and when did you get started?
So Brownie Bee was developed in a 3-year project collaboration between us at DTI, Novo Nordisk, and a third or second research and technology organization here in Denmark called the Alexandra Institute. So they are the people who build the front end, the user interface. They have user experienced designers and stuff, people who know how to make front ends. So they are responsible for the usability. So we had a 3-year project where we collaborated on that, and that was supported by a foundation called the Danish Industry Foundation. So it's a private foundation funded by Danish companies. And so they provided funding both for sort of developing the user interface, but also to support these companies where we implemented it. So to de-risk it for them, basically.
And Søren, I mean, a lot of probably the participants of the webinar, they're interested in some hints on where are you guys at Novo Nordisk heading next, based on what you've showed us thus far. So how does automation come into play? Where do you see applying this to more, for example, the HPLC instruments? What kind of plans do you have?
That's a big question. So if we look at automation, then lab automation, we would typically talk about liquid handlers, and there we have 96 volt plates or something larger than that, which makes at least raw Bayesian optimization not the optimal tool, because you can't get 96 good suggestions out of it. So at least we have to do something else. What exactly to do? We are trying to figure that out and trying different things. HPLCs, that's also a good question. I think right now we have to start with getting the app we have out and people testing it, and then we'll see what people want from that.
Okay, we still don't have any Q&A, so I'm going to ask my final question, and this will take us all the way back to the intro slides that I showed. So we think about traditional DOE. I think I saw somewhere in social media about waves of development in DOE, right? So we had the first wave when Fisher came up with factorial designs in ANOVA, and then the second wave when chemists started working with statisticians in the 50s. So will we account data scientists or computer scientists working with chemists through, for example, BO as the third wave in DOE? What's your take on that?
So I follow a guy from Jump called Phil Kay on LinkedIn, who's quite active there as well. And he just recently started a podcast together with a company called Synthase, who was also very active in the DOE automation space for chemistry and biology. And they were talking about so far the 4 phases of DOE. So maybe there's one in between here that you're missing. But I definitely think there is sort of Bayesian optimization in itself, or the models aren't new. The math has been around for a long time, but it has sort of been rediscovered by the machine learning and AI community and sort of worked its way backwards to physical experiments. So I think sort of that reuptake of something that is very iterative and not completely model driven is fair enough to characterize, and I think it will be characterized in the future as a wave that flushed across the DOE space. Whether it's the third or the fourth or the fifth, I'm not going to be the judge of that.
How about Arta? Do you want to give your inputs on this? What's your perspective from the university? I mean,
no, I tend to agree with what Morten said, that I mean, there's a lot of these rediscoveries happening all over the place. And like, for example, my own background, I mean, I've been much more familiar with Bayesian optimization and that kind of techniques well before I had even kind of studied in any way that how is the empirical science done, like classically. If you think about like where we're going towards in the future, so I think I tried to outline one direction where it is like this much more open-ended problem settings, that it's where the kind of interplay between whatever we do with the algorithms and whatever the domain scientist knows and does, it's just getting more and more complicated. If you think about like in the way of like for example, even having a chat interface where you talk with the partner that's trying to somehow help you. So that's one end. Then, of course, some other people would like to say that we're just going to automate everything. Like just start cranking out more and more data. And that's not going to help. So I think that the fundamental issue here is that we've been able to recently solve some problem, like language understanding, image generation, even like protein folding, by just collecting massive amounts of data. But for new discoveries, essentially, it's exactly that. What's going to happen in my local neighborhood, in my system? How do I control this? This is never going to be a large data enterprise. So this is I think is one of the things that makes it very interesting, that it's very fruitful research direction of what can we do with more and more flexible tools that we now have, while we are still fundamentally constrained by this ability to do 25 or 60 experiments. And I think we can do a lot of things with those. So it's going to be some sort of foundation models that try to grasp more and more understanding of basic physics or basic chemistry. And then how do we use those embedded into a loop where we then get actual concrete experiments on what we do. So I do think, I also wouldn't know which wave of these methods is, but I think this is where it has to go.
Thanks, Arto. I'll take that as our cue to end because our time is up. I want to once more thank all of our speakers. Thank you, Arto, Morten, and Søren. It's been great. And then I want to thank also all the participants. And you can find a recording of this webinar afterwards, I understood, in the FCAI website. So thanks once again, and until next time.